This presentation is based on research and development conducted by Team CoSTAR at NASA's Jet Propulsion Laboratory and the California Institute of Technology. We will be presenting the results of Martian Analog testing with our autonomous quadrupeds and on a mission concept that we call Mars Dogs, which are biomimetic robots for the exploration of Mars from its rugged surface to its hidden caves. The Martian surface is a hostile environment for anything biological. Lack of a magnetosphere and substantial atmosphere result in varying diurnal temperatures and radiation bombardment. The result is an environment that is harmful to any potential organisms and their remains. The environment in which we have historically searched likely does not contain evidence of Martian life, even if it existed at one time. Therefore, we are encouraged to turn our focus to Mars's subsurface, which is sequestered under thick layers of rock. As a result, these environments may have potentially preserved the ancient Martian geologic weta past. It may have also preserved biosignatures, chemical or physical remnants of organisms that may have one day inhabited the red planet, or even extant active organisms alive deep in the Martian underground. Martian lava tubes are an ideal candidate site for habitation of future human colonies. A habitat constructed in a lava tube would not need to be equipped with the various safety measures required for a surface hab, namely radiation shielding, thermal regulation, and dust mitigation systems. A cave would provide these protections naturally. Additionally, ISIU opportunities within the cave would allow for water, oxygen, and fuel synthesis. Our team's current flagship research platform is a field-hardened, artificially intelligent quadruped. We call it Autonomous Spot, or AUSPOT for short. We use this robot for Martian analog testing due to its robust mobility, operational range, and payload allowance. The base-legged platform from Boston Dynamics provides a robust mobility controller that enables it to easily tackle challenging obstacles. NASA JPL's Team CoSTAR has endowed this platform with higher levels of autonomy, which was part of the solution that won the urban circuit of the 2020 DARPA Subterranean Challenge, the most competitive extreme exploration robotics challenge in the world. The autonomy payload, called NeBula, consists of a custom sensor package, which enables perception in GPS-denied, perceptually degraded, dark, dusty, foggy, and self-similar environments. It also consists of a custom power and computing core, which enables real-time, onboard processing of sensory input to autonomously explore and navigate, and it consists of a custom communications deployment system, which enables the robot to form a comms link back to base from within subsurface caves and buildings. Our networked belief-aware perceptual autonomy package, or NeBula for short, is the end-to-end solution that we have utilized from AUSPOT to make Mars Dogs self-reliant. Its system architecture is shown in this chart. AUSPOT's interface provides sensory measurements from NeBula and from Spot's inbuilt sensors, and conversely, it facilitates actuation commands. The sensory measurements go through several odometry algorithms such as LiDAR, visual, thermal, and kinematic. They are then fused into a single odometry output. The global inference builds a detailed 3D topological, geometric, and semantic map of the Martian analog lava tube and learns high-level information such as heights of openings, negative and positive obstacles, potentially slippery surfaces, scientific objects of interest, and much more from the environment. The Belief Manager is the core component of NeBula, as it maintains the robot's model of the environment and quantifies confidence and uncertainty of incoming information. The mission planning switches between various behaviors such as ingress or egress, extreme Mars walk, recharging, and science gathering, and coordinates mission tasks between other Mars Dogs in the robot pack. Global planning guides the coverage behavior to rapidly map and navigate the environment. The local planner assesses traversability risk and plans safe, local goals for the Mars Dog. The communication module enables scientific and telemetry data transfer between the subsurface robots and the lander on the planet's surface. AUSPOT has no prior knowledge of this cave, and so it begins by scanning the unknown environment and initializes the exploration mission. It passes by a target placed there by the team to simulate scientific objects and identifies it with high accuracy. AUSPOT enters an open space and identifies the most ideal path. Over the course of the mission, AuSpot will build a representation of the explored environment that is rich in topological, geometric, and semantic information, some of which is shown in the overlay. This will allow it to remember forks in the road, for example, that it has seen before but not yet explored. AuSpot continues down this branch of the lava tube, examining the walls for points of interest along the way. It again comes to an open space with several different paths. It chooses the path which contains a red anomaly. It examines it, and returns to the fork it identified earlier. AuSpot plans perceptually aware local trajectories to efficiently cover the entire space. While exploring the environment, AuSpot scans and determines where it believes to be safe to traverse without risking physical damage to the robot or lengthening the mission. AuSpot is able to handle high slope ramps, positive and various negative obstacles such as holes and ledges. AuSpot then heads to a wider space and identifies several other targets along its way. It spends some time here building its map and making sure it has covered all angles, and also computes the certainty and accuracy of several anomalous identifications. It eventually decides to move on and chooses to return to its initial node, identified as a fork. But this time, it travels down the previously seen but unexplored passageway. It successfully computes that this pathway also links up to the path it traversed earlier, therefore closing the loop. The completed roadmap can be seen in the overlays. The previously seen lava tubes are thought to be analogous to observed cave formations on regions of Mars, including hundreds that have been identified in the Tharsis volcanic field. The high elevation in these regions provides different challenges for EDL, compared to the rover landings at Jezero Crater with relatively low elevation. The map pictured here denotes regions on Mars with differences in elevation. Grey is above 2 km and inaccessible by landing. Yellow is between 0.5 to 2 km, which is riskier but possible for landing. And green is below 0.5 km and readily accessible. A mission to lava tubes requires both the selection of a landing site that borders inaccessible regions, such as those pictured here, and a robotic platform capable of traversing the distance from the landing site to the caves themselves. Typical platforms would be too slow to accomplish this task in any meaningful time, and thus we require the use of a novel robot capable of a faster expedition. Our preliminary models show that a Mars dog will be over 12 times lighter and far smaller in volume than the current rovers. We propose a 4-phase novel mission architecture following the EDL. Phase A in this mission involves a pack of Mars dogs embarking on a long journey across the Martian surface of up to 100 kilometers or more, collecting unprecedented scientific data along their way in rocky and traditionally unexplorable surface regions, reaching momentary top speeds of over 5 km an hour compared to 0.14 km an hour by the Curiosity rover, while simultaneously mapping topology. We call this behavior the Mars Walk. High-speed travel across the Martian surface introduces a bold but calculated risk, especially when dynamically traversing treacherous regions. Unlike if it were to happen to a rover, toppling does not mean mission failure. By utilizing recovery algorithms, the platform is able to self-right from a multitude of unfavorable configurations. Our preliminary models indicate that with the appropriately tailored milli-MMRTG power core and wireless charging and intelligent walking behaviors, Mars dogs can maintain the necessary energy efficiency to cover the distance between Phase A and B in a matter of months. Once the Mars dogs have arrived at the cave pit of interest during Phase B, they will prepare for Phase C entry into the lava tube. If the robot believes that the ingress presents high risk, it will employ one of its collaborative tethering behaviors and use its manipulator to hitch itself to the other robot. Otherwise, the Mars dog will proceed by itself into the lava tube untethered. During Phase C, the robot will carefully ingress, breaching the planet's subsurface. Our Martian Analog tests in Northern Californian lava tubes demonstrated that the platform can successfully traverse and navigate boulders, a steep rocky ramp, and man-made stairs, untethered. The team intends to perform further research into Orspot's tether behavior capability by pushing the current state-of-the-art technology developed at NASA JPL and Caltech, such as Axle, and adapting it to our platform. During Phase D, the Mars dog will autonomously explore the depths of the lava tube, a behavior we have successfully tested numerous times. It will use its spectroscopic instrumentation for standoff and direct contact-based analysis. The scientific payload will focus on biosignature detection and geologic analysis using remote tools. Further R&D will endow the Mars dog with sample caching capabilities for more advanced analysis back at the Surface Landers Laboratory. We've demonstrated the successful performance of autonomous extreme traversal of rugged Martian Analog surface sites. We've completed successful ingress and egress of complex cave pits in Northern California, and we've seen the robot perform self-reliant autonomous deep cave exploration and mapping of lava tubes several times. These behaviors could one day enable revolutionary scientific missions to take place on the Martian surface and subsurface, thereby pushing the boundaries of NASA's capability in exploring traditionally inaccessible sites. The research significantly advances full onboard autonomy capabilities of the current state-of-the-art in autonomy solutions for Earth and space exploration. Thank you for your interest in our work, and if you have any questions, please feel free to contact us. For further details about the components of our solution, our references are included below.